Hi everyone. Today I'm gonna give you my final lecture on the section on bending deformation. Before talking about new concepts, let me give you a review as always. So in previous lecture, we covered the three topics. First topic we covered was reinforced concrete. Of course, in real serious design of concrete, yeah, we have to involve quite complex mathematics. However, by making two assumptions, which somehow enable very conservative design of reinforced concrete, we were able to simplify the design of reinforced concrete process. So the assumptions we made was following. So the first assumption we made was concrete is completely useless under tension. So that we made assumption that like under tension, concrete has like zero modulus and zero strength. That's the first mathematical simplification we had. And second thing is we assume that steel is very very thin, so that when we account for I, the area moment of inertia for steel beams, yeah, we consider that the I with respect to centroid of steel is 0. Okay, and we only accounted for area multiplied by distance square, which is the second term in parallel axis theorem for accounting the steel's contribution on I. Okay, so these are the assumptions we made in our textbook, and based on that, we went through following process for designing the steel reinforced concrete or 철근 concrete. So here's the geometry we considered in previous lecture. We considered the beam of width b, and we set our location to unknown location x, which is the distance from the top to neutral axis as x. We know the distance between the top surface and the steel beam as d, and we consider overall area of the steel, like these three area together as as. Then based on assumption 1, because we say that concrete is completely useless under tension, we only account for concrete in the compression part, and we only consider steel for the tension part. And from the definition of centroid, of course, yeah, we convert steel into the equivalent concrete using this ratio and ES over EC. Then based on definition of centroid, yeah, we are able to derive equation that determining the position x. Okay, after solving for x, then what we can do is we can set the y equals 0 position, the origin, and after figuring out y equals 0 position, yeah, we have two sections. First section has its centroid at halfway here, so we have the I of first section with respect to its own centroid, which is first term. Then we have to obtain the I with respect to our neutral axis. So we have to multiply a and d square. D must be x over 2. Then based on parallel axis theorem, we obtain contribution of upper block for obtaining I with respect to this axis. Then regarding the obtaining the steel contribution, because we assume that steel is very thin, so we approximate this as 0. Then we only account for area of this guy, which is n times as in equivalent concrete problem, and we multiply d minus x square. Then we are able to obtain the I. Okay, after obtaining centroid position and I, then next thing is very standard procedure. One over rho is m over ei. Then we can obtain the strain distribution very easily. After obtaining strain distribution, if you multiply the modulus at specific position, you can obtain stress at that point. Okay, so this is something you have to remember, that strain under pure bending is very simple. It's a linear distribution in y. After discussing about reinforced concrete, we discussed about eccentric loading. So eccentric loading is like where the line of action does not go through the centroid of the section. So when you take this imaginary section, you can imagine the normal force is necessary to make a force balance. However, if we only have a normal force n, it'll induce clockwise torque to the part. You need counterclockwise direction torque m, so that you can balance out force and moment together, or force and torque together. So from the normal force n, you're gonna have uniform stress. From the m, you're gonna have like a linear stress. Then if you draw the summation of them, you're gonna find that sigma xo equal to be 0 point, which is the neutral axis. Now it's not same as centroid axis. Okay, so when you draw these kind of equations, and when you use the flexural formula, you have to set y equals 0 as a centroid. And typically in pure bending problem, centroid turns out to be sigma x equal to be 0 point, as in this problem. However, when we consider eccentric loading, where we also have the non-zero normal force n, we're gonna have this kind of result. Okay, so please have this in mind. As a third topic, we discussed about asymmetric loading, like when we have this kind of cross-sectional shape. When we apply our m vector in this way, then we can say that as asymmetric loading. And based on the force and moment discussion, what I have found is, to have the symmetric loading, we have to have our axis, y and z axis, satisfy integral yg dA equals to be 0 condition. Okay, and we call this as I, y, z, and we call coordinate system satisfying this as principal axis. Okay, and as an example, I gave you these two set of coordinate system, y prime g prime system and y g system. Given the exactly same cross-sectional shape, you can take y prime g prime in this way, or you can take y and g prime, y and z axis in this way. Okay, so we found that when you take y prime g prime in this way, due to the asymmetry of negative region and positive region, this integral turns out to be smaller than 0, so that we can say that y prime g prime axis are not principal axis. However, when y and z are located in this, I would say, plane of symmetry, then yg negative contribution and yg positive contribution cancel out in entire cross section integral I yg, so that we can conclude that yg are principal axis. Okay, and for this axis, y and z axis, if m is either parallel to y or parallel to g, we can say that m will be on the neutral plane. Okay, so that was the conclusion and the final discussion we had in previous lecture.